Hello and welcome to Electronics with Emrys. In this video, we're going to be talking about translation. No, I'm afraid I can't really help you out with that kind of translation, but I can help you out whenever you need to convert between different voltage standards for single-ended communication. For example, if you have a microcontroller that has to work at 3.3 volts and a sensor that has to work at 5 volts, we can get those two to talk to each other without any problems. Let's start out by talking about down translation. Down translation is taking a higher voltage and sending it to a lower voltage device. If I wanted to send a signal from a 5 volt device to a 1.8 volt device, then that could possibly damage the 1.8 volt device. So we need some way to convert our 5 volt signal to a 1.8 volt signal. This is probably the simplest voltage translation circuit that you can make. It's just a voltage divider, so if we put in 5 volts on the left, we're going to get out 3.3 volts on the right. I created this simple test circuit to allow me to check out all of my different translators in the same configuration. On the left side, I have my signal sources. So the first one, VG1, is a square wave and VG2 is a triangle wave. Both of these output 1 volt, and then that gets converted through the voltage-controlled voltage source to be whatever voltage I'd like. So in this case, I'm multiplying it by 5, so I'm going to get a 5 volt signal out. I added a 50 ohm resistor to make that a 50 ohm source, and then that's going to be put directly into my voltage translator circuit, whatever that is. I put a couple of extra things into my voltage translator circuit just in case. I'm able to put in a low side voltage and a high side voltage, as well as ground. So I won't be using those in all of the circuits, so you'll see in my particular circuit diagram how it's connected internally. On the right hand side, I have a load, which is basically a CMOS input with 1 mega ohm of leakage and a 5 picofarad capacitive load. My first circuit to test is the voltage divider. This is the output from the voltage divider circuit whenever I put in 5 volts. At the top, you can see the input for the 5 volt square wave is 5 and 0, and the output is 3.3 and 0. Exactly what we want from a translator. I added this triangle wave so we could see what happens to the signal whenever it's not exactly a square wave. In this case, for a voltage divider, it gets scaled exactly the same. So we start out with 0 to 5 and we end up with 0 to 3.3. So basically what you'd expect. And in future circuits, we'll see that's not always the case. If I just change the input voltage to 10 volts, we can see one of the main problems with a voltage divider input. And there you can see that we're no longer outputting 3.3 volts. We've increased to 6.6 volts, which is of course what we would expect to see if we double the input voltage on a voltage divider. But if we had a change in voltage in our system, even if it was relatively small with a voltage divider, the output of our translator would also change. And that can be a big problem for some systems. So you got to keep that in mind if you're going to use a voltage divider for down translation of voltages. This next circuit works a little better if you have voltages that go outside of the range you expect. So I went ahead and kept the same resistor here. It doesn't really matter what value I put here as long as it's large enough to not damage the diode. This is called a positive voltage clamp. The idea is whenever your input voltage goes above VCCB, eventually it will turn on this diode, and that will prevent your output from getting to too high of a voltage. Just to show you how I'm changing out these models, all I have to do in Tina is right-click on this Spice macro and go to Enter Macro. And then I can change out the code in here. So now I've got my diode clamp model pasted in here, and it's using the same pinout as the other model that I used previously. And here you can see that I'm getting from a 5 volt input dropping down to just below 4 volts on the output. The triangle wave gives me a little bit better idea of what's going on. Like I mentioned, as we increase our voltage up, eventually it starts to clamp out, and that actually causes a change in the waveform for the triangle wave. Let's go ahead and change the voltage up to 10 volts and see what this does. Here you can see that it's a much more pronounced cutoff whenever we increase the voltage. So as we go well above 5 volts, it remains at about 4 volts on the output. So now if we wanted to have this be exactly 3.3 volts, what we could do is change our VCCB value. Basically, you just want VCCB to be one diode drop below what you want your output voltage to be. So in this case, it would be 2.6 volts. And now you can see even with our 10 volt input, on the square wave we're getting 3.26 volts, and on the triangle wave we're getting 3.25 volts. So both of them would work very well for a 3.3 volt input without causing any danger to the device. I would say one of the main drawbacks to this circuit is that it's going to require that there be some current flowing back towards VCCB. And a lot of circuits will not like it if you start sending current back towards the supply, because typically supplies are designed to provide current to a circuit, not to sink current from a circuit. This next circuit is exactly the same thing. We're just changing out the diode for a Schottky diode instead of a regular diode. And here you can see that the Schottky diode has a much lower turn-on voltage, so it actually clamps at a lower voltage whenever we use the same VCCB. The output's only making it up to 3.07 volts, which would still probably be fine for most 3.3 volt devices. If we wanted to get that up closer to 3.3, all we have to do is change our supply VCCB up to 2.8 volts, and we can see that. And there's our output with 3.27 volts in both cases. Now, if you don't want to use a positive side clamp because you're worried about the current going back to your supply, then you could use a ground side clamp. In this case, I've selected an LED that gives me an output voltage of about 3.5 volts. You can get LEDs that go all the way down to about 1.8 volts, and they go up to around 4 volts. So it kind of depends on which LED you pick out specifically for the application. Similar to the LED, but with more variety in voltages available, is the Zener diode. A Zener diode is designed to be connected up in a reverse polarity. So now, whenever the voltage reaches a certain level, it's going to activate the diode in reverse and allow current to flow through it. The diode will naturally regulate to its reverse breakdown voltage. Here you can see that with this Zener diode, I'm getting 3.14 volts at the output and 3.1 with the triangle wave. The one big downside I've found with Zener diodes is that they tend to have a pretty high capacitance associated with them, especially at lower voltages, so these can really kill out faster signals. This is another type of clamp circuit, this time using a BJT. Basically the way this works is you're applying a positive voltage to the base, so whenever the input is 0, or a small voltage, then the transistor is biased on and it will be pulling the output low. Whenever the input starts to approach the same voltage as VCCB, then this transistor will turn off, and that will cause the pull-up resistor on the other side to pull up to VCCB. You don't necessarily have to have the pull-up resistor, but if you don't, then the voltage at the output won't be as high. It'll be about one diode drop below the voltage that you want. Here you can see one possible issue with the BJT is that the output voltage can overshoot past the voltage that you want it to be, which would be, of course, very dangerous if you're trying to have a down translation that's protecting something downstream. I believe this is primarily caused by the turn-off speed of the transistor. You can see that it doesn't happen with the triangle wave, so a slower signal doesn't cause that same issue. And if you increase the resistor on the base, it also reduces this effect. So if you have really fast signals, then you would need a really fast transistor to handle this. This next circuit changes out the BJT for a MOSFET, and it works basically the same way. One thing to watch out for with FETs is that they have an intrinsic diode that's going to connect the source to the drain in this way. So you definitely want to make sure to connect it the right way around, otherwise you'd be connecting your input directly to your output through a diode. And in my simulation you can see that I'm getting exactly 3.3 volts at the output. In this circuit we've connected up a BJT as an inverter. Basically if the input is high enough, greater than 0.6 volts, then the output will be pulled low. When the input is lower than 0.6 volts, the transistor turns off and the output is pulled high by the resistor. The size of the resistor up here decides how strong the output is driven to the high state. And the resistor at the bottom determines how strongly the transistor turns on whenever the input is in the high state. If you see a device that says it has open collector outputs, then they basically have this same setup. The resistor would have to be connected externally to pull the output high, but the output would just connect to the collector of a BJT like this. And in the simulation, you can see that whenever the input is in the high state, the output is in the low state. But even though the output is inverted, it is converted to a 3.3 volt signal from a 10 volt signal on the input. You can see on the triangle wave that the signal is transferred a little bit to the output because the BJT will act as an amplifier for a small region of the input voltages. But for a square wave, it works perfectly fine. If we trade out the BJT for a MOSFET, we get basically the same circuit, but now no current goes from the input into the MOSFET. Generally speaking, you still want to have a resistor here because there is a significant amount of gate capacitance on a MOSFET, and whatever you're driving that input with, you want to protect from overcurrent as it charges the gate of the NMOS. After running the simulation with the MOSFET, we can see that we get the same results. The output is inverted, although with the triangle wave, we get a bit of a cleaner output with the MOSFET than we do with the BJT. It has a higher gain, so it's going to produce a sharper edge. One big difference between BJTs and MOSFETs whenever it comes to this circuit is the turn-on voltage. BJTs generally turn on around 0.6 to 0.7 volts, and MOSFETs generally turn on around 1 volt or higher. So if you're looking to convert really low voltages, a BJT may be a better choice. Last but not least for the down translators is just using a buffer. There are many buffers on the market that can be used as down translators. It's important to realize that some buffers have a diode like this that's inside of the buffer. If you check in their datasheet, they should tell you that you can't go above the VCC value because of this diode. There are also many devices that don't have that diode, and so you can actually drive the input voltage higher than the supply voltage without any danger of turning on that diode. One example would be the 74LVC1G34. It's a single gate CMOS buffer. And here you can see the results from the simulation with a buffer like this. Generally speaking, the results are very good. And the one thing you really have to watch out for is that the inputs on these have limited capabilities. In the datasheet, it'll tell you what the absolute maximum input voltage range is, and many times it's going to be 5 volts. Sometimes it can be very beneficial to use one of the previously mentioned down translation circuits in order to protect the input of a CMOS buffer like this, and the buffer itself is what's going to produce a nice clean square wave output. One thing to mention is that generally speaking, CMOS devices don't like slow transitioning inputs. My simulation shows a very perfect output from a triangle wave input. Many times you'll see an oscillation on the output if an input is as slow as this. So if you do have a slow input, generally speaking, you'll want to choose a Schmitt trigger device like the LVC1G17 instead of the LVC1G34, which is just a standard CMOS device. This circuit would actually be my first choice whenever I was building a down translator for a professionally developed system. However, if I'm building something at home, then one of the other circuits is more likely to be what I'm going to use. There are other specialized translators out on the market, but most of them utilize one of the circuits that I've shown so far. You can also use a device like this for up translation. The input signal to a logic device isn't always perfectly at ground for a low and supply for a high. In a typical CMOS logic input, you have a VIH and VIL provided by the datasheet, and somewhere between them is the threshold voltage where it actually changes states. As long as your input is lower than the VIL voltage, then the device will detect this as a low input. As the voltage rises from VIL to VIH, there will be some point where the input is detected as a high instead, which is what we call the threshold voltage. There's still a bit of room before we get to the VIH voltage, which is the guaranteed high state voltage. So an ideal up-translation device would let you keep the same VIL, but move the VIH voltage down, giving you the ability to input a much smaller voltage and still have it get detected as a logic high. Now I know this looks exactly like the other CMOS buffer that we were just talking about, but thinking about the input thresholds, these are different from the original device we had discussed. So with a normal CMOS input, the threshold is about half VCC. But this is a TTL compatible device, so the input threshold is actually closer to 1.5 volts. You can see in the simulation results that my input is a 2 volt signal, but my output is a 5 volt signal. And on the triangle wave, we can see where that's actually switching. So the input goes from low to high right around 1.5 volts. You could probably use a TTL compatible device for a 1.8 volt input to get it up to 5 volts, but it's not usually recommended because there's not enough margins there for safety. But there are many translators out there on the market that utilize this same reduced threshold input voltage system and allow you to change the supply voltage. So for example, you could be running at 3.3 volt supply, and with the same input signal, you can see now that my output puts out 3.3 volts, and my triangle wave is switching at a very different point than it previously was. So now instead of switching at 1.5 volts, it's now switching closer to 1 volt. This reduced input threshold allows you to do up translation pretty easily. There is one downside to this, and that is increased power consumption. If you go pull up a datasheet for one of these devices, you'll find that TTL compatible devices pull a decent amount of current whenever you're not putting in a voltage that's all the way at the rail. So generally speaking, with CMOS devices, you want your input voltage to be the same as your supply voltage, and that reduces the amount of current shooting through the inputs. TTL compatible devices are designed to operate like this, but they're also designed to have a pretty large amount of current sinking through that input, which can be up to a couple of milliamps, which may not sound like much, but in a logic device, you're generally only going to be getting a couple of microamps or less whenever your device is not switching. Going back to the BJT clamp circuit, we can see that that also can be used as an up translator. Here I'm putting in a 1.2 volt input signal and getting out a 5 volt signal. Now, it is important to note that my output here is about 1 volt whenever we're in the low state. So that is a bit higher than what you'd usually want to have, but it's definitely better than nothing if you don't have any other option for a translator. You can also use an NMOS clamp in the same way, and it does an even better job. You end up getting about 100 millivolts on the output in this case. Now, one thing that's really important to remember is that this 100K resistor on the output is what's pulling up to the supply voltage of 5 volts. That means your output is very weakly driven to the high state. You can improve this by reducing this resistor value, but the more you reduce this resistor, then the more current will have to sink into your input device. So there's going to be a balance between how much drive strength your input device is able to handle and how fast your output needs to be. And the fact is that many times this circuit won't work very well for high-speed signals. You'll most likely have to go to a dual supply translator, which will be the last one we look at. The open collector circuit can also be connected to a higher voltage on the output than on the input, allowing you to do up translation. Of course, you still do get an inversion in your signal here, so that's important to remember. But we are getting about 0 volts in the low state and 5 volts in the high state. Similar, the open drain device is able to do the same thing. We get an even better output signal, and we're able to convert from 1.8 to 5 volts without any problems. We just get that inversion. And finally, you can do up translation with a dual supply translator, something that's an IC that was developed specifically to take your input signal from one voltage to another. These require that you have both supply voltages available in your system, which is usually not a problem. And they also generally have voltage limitations, many times only being able to go up to 3.3 volts or only up to 5 volts. So these are really what you use whenever you need a high quality signal at a high speed for a very particular application. I briefly showed this at the beginning of the video, but these are some of the voltage standards that we commonly have to change between whenever we're communicating with different devices on a PCB. These days, 3.3 is probably the most commonly seen signal level for a microcontroller. The outputs of your device are going to be putting out around 3.3 volts as long as you're not driving any heavy loads, and 0 volts in the low state. So that means you can probably get away with sending a 3.3 volt signal into a 5 volt input. You can see that that's above the threshold value, but it's not all the way up to the VIH value, which is the recommended input voltage for that device. Sometimes people make mistakes and connect things up and then wonder why they're working when the datasheet says they shouldn't. Many times it's just a misunderstanding of what the device is capable of versus what the datasheet recommends you do with it. I hope that this video has been informative for you if you're going to be working with multiple voltages inside of your system, and has given you a few different tools for your toolbox to be able to develop circuits for whatever it is that you're working on. If you have any questions or concerns, please post them down in the comments. Thank you very much for watching, and I hope you have a great day.